There is a meeting in the Great Hall going on close to me, so if you hear background noise, that's what it is. I don't think they're
Okay.
going to kick me out. We'll see. But just so you know.
Okay, thank you.
So, did you have particular questions for me?
Uh, yes.
What's up?
On homework 18, exercise 1, part C. I think I got it right, but could you go over that just
On homework, which one?
to make sure?
Let's see. So, which homework did you say it was on? It was on homework 18?
Homework 18. Yes.
And then example, or not example, pardon. Problem, you said 2?
Problem 1,
Problem 1.
part
Okay.
C.
Okay, cool. Let me go ahead and open that up and see what it looks like. 1C. Assignments. There we go. 18. Okay, 1C. And you're asked to convert it to machine code. Okay, so what was your question for that?
Um, I just want to make sure that I did it right.
Okay.
I guess it's more specifically on the offset, I think. Because it's you're subtracting the bigger one, which in this case would be uh the jump in link going back, and then the back label, right?
Yeah, you always do the label location minus the jump instruction location, and that'll give you the offset. So you always subtract. You always do the label place minus where the instruction was. So if the label occurs before where the instruction is, then that means you're going to have a negative offset. So you're jumping backwards in code.
Sorry, you're kind of stuttery.
Oh, am I? That's very strange. Oh, that makes sense. It's not fully charged. Okay, that's fine. The stuttering hopefully will stop a little bit later. Did you hear my answer to your question about the offsets or no?
Yes, it would be a negative offset.
Yeah, it would if it was jumping backwards. Yeah.
Oh, okay.
What was I gonna say? Do I assume that wasn't your only question about it, or was that the only question you had?
Um, Aside from just like getting the answer, because I don't know if I did it correctly.
Right.
Um, I, but my only question for that would probably just be like, uh, the offset would be a negative value because it's going back
Correct.
up.
Yes, that's right.
Yeah.
And it's pretty helpful to just have the what's it called Appendix B open whenever you're doing any of this stuff, just because no one wants to memorize the instruction formats. So for JL, do you remember what type that is?
Yes, that's it's a J type.
I believe that's correct. There are a few that are a little confusing in that they are not what you'd assume they would be in terms of their
Mm-hmm.
typing. I can't remember. There's one that's a U type that we call a jump instruction, if I recall correctly. That's very backwards from what you'd expect, but I need to check. Let's see. I don't know. Well, some interesting ones like load up or immediate is, funnily enough, not an immediate instruction. It's not an I type. It's a U type. because you have to encode a very big immediate value. What's the other one? Oh yeah, jump and link register, JALR, interestingly enough, is an I-type, not a J-type, which is a pretty funny one. And there are a whole bunch of others that are a little backwards from what you'd think. But anyways, yeah, for jump and link, which is the one that you have in this homework, that one is going to be J-type. Yeah, that looks good. The stuttering, I don't know if it's still going for you, but the stuttering should stop in the next, hopefully, like 10 minutes when my computer's fully charged. Sorry about that.
No, you're fine. I think it's good now.
Okay. Did you have any other questions for me?
Yeah, just one really quick question.
Yeah.
Would you happen to remember for the test, like, she said that she's gonna give us Appendix B. Is it going to be all 4 pages of this, or just
It's
the
gonna
ones that's
be-
relevant?
It's only going to be the stuff you need. I think, if
Oh,
I
okay.
recall correctly, it'll have all of it on there. I think she'll just print them all. I may be wrong, but no matter what, it's just going to have the relevant information. So, for example, the second half of page 2, you're not going to need that because you guys aren't doing any floating point instruction stuff. You don't have to concern yourself with that. And probably the second half of page 3 you wouldn't need as well because that's compressed instructions. You're not going to be messing with that stuff. But my guess is she'll just print it all out and then put it on the back of your... Because what she did, if I recall correctly, what she did for when I was taking the classes, she just printed all of the appendix pages out and just stapled it to the back of the test. And so you have access to all of them.
I see. Thank you. Aside from that, I don't have any more questions.
Cool. What's it called? What did you guys go over in class today? Because I know you guys' midterm is coming up quite soon.
Yes. So we did a quiz, and then she just finished the rest of her slides for chapter 6. Let me see. She went over Big Indian and Little Indian.
Okay. That makes sense.
Mm-hmm. But I believe...
Okay. How are you feeling about the midterm coming up? Do you think you feel confident on the material?
I think so, because the hardware portion of it, like if we were asked to like draw a schematic for maybe like a counter or multiplier, that's not. I don't think it's too difficult. And I still remember going over it, so I think that's a good sign.
Right. Okay, that's good. So AJ's asking in the chat if we can talk about problem 2. So I'll start it off. I'm probably not going to go through the entire thing because it is a lot of decoding to do. But I'll basically show you maybe 1 or 2 of the lines and talk to you about how you're supposed to approach these kinds of problems. So the first thing you want to make sure you're doing for this exercise is you want to have your Appendix B on hand, because the very first thing you're going to need to do is you're going to need to take this and separate out the bits and figure out what all the bits correspond to. So I'll go ahead and write the the machine code for this first line, for the instruction on that first line there. So we have 01800 So that's the machine code. And what we care about is the different sections of the machine code, the different fields, which correspond to letting us know what kind of type we're dealing with and what instruction we're dealing with. So the first thing you're going to want to do is take a look at the opcode. That's for any instruction. You always take a look at the opcode, which is the bottom 7 bits of your encoding. So in this example, the bottom 8 bits are 0001, that's from the 1, and then 0011, that's from the 3 here. And so you take a look at those bottom 7 bits, which is the sequence 001, 0011, and you try to match that up with what type it's going to be in your appendix. So in this example, this is what's it called? In decimal, this is the number 19. And the reason why I bring that up is because over on your Appendix B, it has the opcode in binary, but it also has the opcode in decimal next to that. So we can just look for all the 19s, and we can use those to tell us where to look. So all the 19s are immediate types. So you'll notice that it starts with the add I instruction, all of those, all the way down to the and I instruction. So all of those have the same opcode because they're all immediate I types. So we know that because of this opcode, we know we're dealing with an I type. Okay, so any questions on that? It might be a little in the way. So we know it's an I type, and now the next thing we need to figure out is what the rest of the fields hold. So I'm going to go ahead and draw the immediate encoding, or not the immediate encoding, sorry, the total machine code encoding for the I type instruction. I'm going to draw that on the board, and then we can separate out each of those bit fields. So for the I type, opcode, we have 6 to 0. That's the bottommost spot. And again, I'm getting this information from Appendix B. Right above that is your destination register, so RD. Opcode is 7 bits, RD is 5 bits. It goes from 11 to 7. And then next is the funct3 field, which it's called funct3 because it's 3 bits. I'm going to abbreviate it as F3 just so I have extra space. And then next, after the funct3 field, for the I type, I have RS1, which is my first source register, and that is 5 bits as well from 1915. And finally, all of the rest of my bits are just for my immediate encoding. So that's over here, 31 to 20. So all of those bits. And inside I have my immediate encoded in 12 bits of binary, so 0 to 11 to 0. And this consists of 12 bits. So if we double check and we add all these up, 5 plus 5 is 10, 3 plus 7 is 10, so that's 20. 20 plus 12 is 32, so that's all 32 of our bits. You say, would it be fun to just convert the entire hex number to binary? And they go, yeah, that's what we're going to end up doing. Yeah, I was just putting this on the board because just to have it on there, I don't have to keep looking back and forth. So yeah, the next thing we would do is we would say, okay, well, what's RD going to be? Well, if I start converting this all to binary, and let me go and do that, I'm going to get the following. I'll do it like this. So 0, 1, 0, 1, 8, 0, 0. Making myself way too much room. 1, 8, 0, 0, 5, 1, 3. And so yeah, I would just then write it in binary. So I have 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, whole bunch of zeros, whole bunch of zeros, 1 followed by a bunch of zeros, zeros followed by 1, and a whole bunch of zeros. So that's the binary sequence which this hexadecimal code is decoded into. And so now I can separate these fields out. So this is the opcode. These 5 bits here is my destination register. These 3 bits here are my funct field, F3. And then these next 5 bits are going to be RS1. And then finally, these 12 bits are going to be my immediate. So now what I can do is I can figure out what these correspond to. So this opcode, which is 19 in decimal, just means that we're doing an I-type instruction. And if we're looking at the destination register, it looks like that this is going to be, that should be 10, so X, register X10. So if you convert this 5-bit number, 01010, into decimal, you get 10. And so if I was to look on my appendix, on page, I believe it's page 3, yeah, page 3, it details which all the registers are. So register X10 is A0. However, just so you know, you could actually type X10 into your assembly code and it would actually understand that. If you were to type that on Venus, these will both work. A0 is just more of a human understandable name, and X10 is more closely corresponding to what it actually is encoding, which is the 10th register, or register 10. But you can type either, and they'll both work. Yeah, I'm just putting both just because I want to be consistent. But when you're actually writing out the instruction, you pick one or the other. You either do X10 or you do A0. And I would just do A0 to make it easier. RS1, which is your source register 1, is the 0 register. So X0, which is the 0 register. And then F3 is all zeros. So the point of funct field 3 is to let me know which instruction within the immediate instructions that I'm going to be messing with. So in this case, we take a look at all of my I-types, which have a opcode of 19. So let's see, we have a few of those. 3, 4, 5, 6, 8. So it looks like 1, 2, 3, 4. Our funct field is 0, which corresponds to the very first immediate on that list, which is add immediate. So this is an add I instruction. Any questions on how I got that from the appendix? Okay, and then the very last thing is this immediate encoding. So I'm going to try and write the number in decimal, not in hex. In decimal, this represents 8, and that's for 16, so in total that's 24. If you were just to convert this into decimal. And so now we have our full instruction, and we can write it out. So we know it's an add I instruction. We know that we're storing something in the destination register. So that's the thing that comes first, A0. That's where we're storing our information. And then the two things we're adding are the 0 register with the immediate, because it's an add immediate. So I'm going to take 0 and add it with 24. And so this is the instruction that would be encoded by this machine code. Add immediate A0 with 0, and you're adding the immediate 24. Every single other one is going to work identically to this. It's just you're going to get different instructions. So your formatting is going to be different, but it's the same process the whole time. So for 3B, It's saying reverse engineer a high-level program that would compile into this assembly language routine and write it. So what's confusing you about what that's saying? Oh, no worries. Yeah, you're just basically uncompiling it. So you've been doing C code, then assembly, then machine code, binary. You're going backwards now. So you're basically saying what C code would have been generated into this. Yeah, exactly. Yep. And then the last question is asking you basically to interpret the code. So like if you're in your CS class and no, you're not done, don't worry. It's fine. If you're like in your CS class and you just look at a function, just like from the name of the function and from the things that's occurring within the function, you can guess as to its purpose. And so the last part of this question is asking you to guess the purpose of this function, essentially. Like, what's the point of this function or this program? And I think that's it. So, any other questions on that? Yeah, it's all good. These particular kinds of the questions where you're asked to decode machine code, or I guess take machine code and turn it back into assembly, are a lot easier than they look, because they look very daunting with all the types and whatnot. But it's really formulaic. It's supposed to be very what's the word? Rote. It's supposed to be very rote because you want your machine, your processor, to be able to decode this really easily. And so hopefully you should also by hand be able to decode it relatively easily. Okay, yeah. Sounds good to me. Did you have any questions on this stuff, Good Noodle? Or are you good?
I have a question for when we're doing branch types. So we have the offset. So do we just code in the offset, even though that wouldn't work in on Venus because it's not a label?
What do you mean?
Okay, so for 0x01c54863, that's a branch type, and so or B type, and then I got the immediate, but then if I were to turn that into a RISC-V instruction, would I just then just do my arguments, and then the immediate encoding, or like do I have to like take a label?
So, see AJ. It was for exercise 2?
Exercise 2, yes.
And then which line was it?
0x01c54863.
Okay, and you said that decoded into a branch?
Yes, a branch.
Yeah, so what you'd have to do is you have to figure out the immediate. So in the case of the branch, I don't remember the ordering for the immediate. Do you remember what you got for the immediate for that one?
Yes, I got 8.
Yeah, so all that means is you'd put a label 2 instructions down from that instruction. So since it's hex 01C5, you'd put a label on hex 00BE0E33. Because that's 8 away from it.
Oh, because it's relative, right?
Yes.
Okay, that makes sense.
Any other questions on that?
No. I'm good, thank you.
Yeah, you're welcome. This is your guys' last homework until your midterm, yeah?
Yes.
Okay. So only studying. Are you guys going over new material in class, or are you just gonna be doing review? Do you know?
In this case, we had so we did like 45 minutes of our quiz. That's how long it took to go over it, and then she just went over some of the slides, but then we went to the part where she said like it's not covered in CPE 200, but it's just content that she wanted to talk about, just in case anyone was curious about it. Yeah, so I guess we finished chapter 6.
Oh, nice.
Yeah.
Really? You guys have already... What? Oh, that's ridiculous. I guess that does make sense.
Yeah, it feels like there's a lot that was omitted, like the compressed instructions, the floating point, registers, and instructions.
Let's see. Just an operand, some other stuff. So, do you know what you guys are going to be going over next?
She made a diagram of something like that I'm not remembering too well right now, but and she said that. Let me see if she made it annotate if she's updated the annotated notes. I don't think she went over what we were gonna go over next then.
Okay. Yeah, there you go. There's the Endianness. I guess Endianness is like almost the end of this chapter, or close to the end, anyways. Let's see. Oh, some floating point stuff at the end, but I don't think you guys are going to go over a floating point. Yeah, other encodings and stuff. Okay, yeah.
Oh, yeah, the
fine.
beat counter. She talked about that.
The stuff at the end that's like not for CP200, but she talked about it.
Yeah, she talked a little bit about that as well.
Let's see, compressed. Did she talk about the compressed instructions at all?
I think it was more of a glance over.
Yeah, it's just some instructions they made encodings such that you can basically, instead of taking 32 bits to encode a single instruction, you can just use 16. So you can get twice as many instructions for the same amount of memory. But the problem with that, or that's not the problem, but you got to keep in mind that you can't do every possible instruction in those 16-bit encodings. You can only do some of them. So you can't just use compressed instructions. And then, did you talk about floating point at all, or no?
Same with the compressed, just like glancing over.
Okay. Yeah, it does look like a pretty, very brief glance. But yeah, she talks about, or at least it mentions stuff about the standardized floating point encodings. So in every encoding in RISC-V, it's following the IEEE standard, which is just for 32-bit floating point operations, you call that single precision. It's called a float in code, so that's why it's called float in high-level code. It's a 32-bit value, whereas double precision, so doubles in high-level code, are 64 bits. So you get more bits to represent basically your number. And there's also quad precision. You're not gonna really mess with that too much, but it exists. It's a thing. A whole bunch of other stuff like the instructions and whatnot. Yeah, nice. That's good. So you did finish up all with that. I'm curious, so I kind of want to look at your guys' syllabus because I cannot for the life of me remember what comes after this. I know I should know it, but I don't remember what it is. Shoot. Oh, that's right. Yeah, adders and stuff. Okay, that makes sense. And so, your guys' midterm review is what's it called? On Monday, yeah.
Yes.
Okay, cool. All right, yeah. Sorry, I was just going off on a tangent there because I was curious. Did you have any other questions for me?
No, not really. I just gotta finish this. It's not homework. Then I got
Good.
math homework. Yeah.
Let me just erase this. Ugh.
I have a question that doesn't really have anything about the homework.
Yeah.
You just took a test recently, right?
Yep.
What was the test about? I'm curious, like the higher level.
It was from my PCB class. So we are learning about how to do high-speed PCB design, which is different from regular PCB design. So you're going to talk about, so it's a lot of like heavy circuit stuff. So like 220, 221, which I know you haven't taken yet. But basically when you draw circuits and you have like a wire, you can treat that wire as being the same voltage along the entire wire. It doesn't matter where along the wire you're at. But for really long wires, or for signals which have super, super fast transitions from being a low voltage to a high voltage, you have them behave not like a wire which is the same voltage throughout, but rather as what we call a transmission line, because the signal has a delay, i.e. it takes time to go from one end of the wire to the other. And so we've done a lot of stuff in terms of PCB things, like having the traces, which are the wires connecting stuff on your PCB, being treated as traces because your signaling speed is super, super quick. And a whole bunch of other stuff, like effects of mutual capacitance and inductances on wires that are coupled together, and things like the effects of ground planes, which are just literally like a big sheet, which is just the entirety of it is held at 0 volts at ground, and a whole bunch of other stuff. But yeah, that's a little bit of what we're talking about. And then now that we finished the midterm, we're going to be working on our final project for the class.
Like, do you have to design for your final project? Do you guys have to design the PCB or?
So the whole point of the class is to get an idea of the constraints that have to come along with high-speed PCB design, so the things you have to consider. So she's not making us make like a full PCB design. She's fine if we just do, because this is with Dr. Harris, she's fine if we do just SPICE files. So LT SPICE is a software you use to simulate circuits, kind of like how you guys use Model Sim in lab to simulate your digital circuitry. You can use LT SPICE to simulate analog circuitry, so stuff with resistors, voltages, and whatnot. And so she's fine if we just do LT SPICE models, but we have to have like a certain amount of signals that we're dealing with, and distances between them in models and stuff, and a whole bunch of things like that to consider. Basically taking all the stuff we've learned and applying it to some system that has to send signals back and forth between stuff. And it doesn't really matter what we do. We can choose to do whatever we want for the design as long as it's high speed and we have a certain number of signals that we're transmitting. Lots of interesting stuff, though, in it that you don't really talk about that much in your undergraduate classes.
Yeah, because like as you were explaining, I was like, okay, yeah, I don't know this yet.
Yeah, I mean, I'm skipping over lots of details, but yeah, don't worry that you don't know it. It's not a lot of stuff that you would end up going over anyways. But yeah, that's what the midterm was on. A whole bunch of stuff. Did you have any other questions for me?
No, I think I'm good. Have a great rest of your day, Victor.
Yeah, you too.
Thank you.
All right. I think I'll post recording then.